Hello, everyone. How are you? I hope things are going well at your end and you all have watched all the videos by now. If still there is anything pending, please go and watch it. And you know what? We are almost halfway done when it comes to organic. So, yeah, it's that way easy. And see, you have learned it in such an easy manner without even realizing that you are doing something which you feel like it is very heavy onto you. Yes. So if I make you recall that when it comes to organic, what we all have done by now. So when I what all we have done today, we have talked about the isomers, might it be the structural isomers or the stereoisomers, with the questions, how the questions has come in the past papers based on that. Then we have also talked about the mechanism in which we talked about the SN1 reactions. We have done SN1 reactions, SN2 reactions with the entire mechanism. Plus, I have told you what is very important in all that, what are the examiners looking for when they talk about the mechanism, and what are the spaces that will be left out where we loses actually the marks. Then we have also talked about the free radical mechanism, the type of fission. Also, we have covered the why the chlorine free radical is able to deplete the ozone layer, why you get chlorine free radical through CFCs, and why not fluorine free radical. So these are all that we have already covered so far. And today, so yeah, we'll start with the addition of X2, where X is basically halogen, could be chlorine, bromine, iodine, right? Now let's take an example that you are converting ethene plus bromine to dibromoethane, right? So let's make the structure. Ethene is CH2, double bond CH2. Now you have to react it with Br, and you are basically forming CH2, CH2, Br. This is the compound which you are actually forming. Now how to form? Because the Br2 react over here is a non-polar compound. So if it's non-polar, it is not going to react. Now, how to make this Br2 reactive? So what happened when this Br2 molecule comes in contact with the ethene molecule? So what happens, since this is electron rich, it is going to repel the electrons of the bromine, which is near to the double bond. So because of that electron repulsion, which this bromine is going to feel, it is going to shift its electron towards the other bromine. As a result, for the duration, when this bromine is nearby to this double bond, will develop a partial positive charge, while the other bromine will will develop a partial positive charge and the other will develop a partial negative charge. So the bromine, which was initially non-polar, has now become polar. So what has happened now? This bromine, the one which is positively charged, will go and get attacked onto one carbon atom, right? Now, since the carbon, both the compound to which we are attacking is a symmetric compound, you can attach this bromine to any carbon no matter what, right? So this is the condition, plus you have something as Br negative left out. Now what will happen? This Br negative is going to attack on this carbocation and form a compound CH2Br, CH2Br. Right? So showing the arrow from the double bond to this halogen is very compulsory. Then this arrow, this partial positive, partial negative. Then showing out this particular bromine going to a carbocation and finally making the compound. And please keep in mind, since it's an addition reaction, you will just have one single product. You don't have any byproduct along. Yes. So since you have the symmetric compounds or an asymmetric compound, you can attach it to anywhere, right? Because since it is the same compound in which the bromine is attaching, basically, like what I'm meant to say is, you are adding the bromine to an unsaturated compound or a chlorine. So whether you add it to a symmetric or you add to a symmetric, there is no change because ultimately both the bromines is going to get attached. Correct? Now, let's come to another addition, which is HX, where X could be any halogen, right? Now we'll do it, let's say, of HCl. We'll take an example of asymmetric and one for asymmetric. So let's do it for ethene first. So basically, this is one a symmetric example. Let me write it down from a bit ahead. Symmetric alkene. Yeah. To this, you are adding HCl and you will get CH2H, CH2Cl. You can attach Cl on the first, H on the second, that's fine, no matter. Now, how the reaction is actually happening. We know that HCl is a polar compound. So electron cloud will shift towards the chlorine atom. And this will become a partial positive and this is partially negative in charge. This partial positive will get attracted by this double bond. Correct? So what will happen? Hydrogen will come and get attached to it. Now you can attach this hydrogen to any carbon in this case. Plus you have Cl negative being left. Now this negative will go and attack to this particular positive charge and will form the compound like this. Correct? Symmetric is fine. It's clear. The same if it would have been happened for an asymmetric compound. Now, what would be the change? Let's say take an example. This. To this, I am adding HCl. Now, again, Cl is a polar bond, right? It will develop a partial negative charge. It will develop a partial positive charge. So, double bond will go and attack onto this particular hydrogen. Now, what will happen? Over here, we use a rule which is called as Markovnikov rule. Now, what does this rule say? It is saying then the negative part of upcoming atom goes to that carbon that has less number of hydrogen atoms. Right? That means over here, if you see, this is 1H, this is 2H. So my negative part, which is chlorine, will go to this part, which has less number of hydrogen atom. So now when I form a cation, my H will go to C. So the H will go to the atom which has more number of hydrogen atom because being an asymmetric compound, chlorine will go to the compound or the carbon which is having less number of hydrogen atom, right? So I will make a carbocation like this, CH3, CH positive, single bond CH3. Now, if you recall and remember, we discussed about the types of carbocation when we were discussing the SN1 reaction. If you have not seen that, please go and watch that. Now, if you can see, this is a secondary carbocation, right? Over here, we know that if you attach this H over this second carbon and this becomes positive, that will become a positive primary carbocation, which is not stable. So thus this will not get stabilized, and this rule was given to us by Markovnikov. That's why it is called as Markovnikov rule, right? So we got this particular secondary carbocation, plus you have a Cl negative. So now this positive charge will attack by this negatively charged chlorine and will finally form a compound CH3CHCl CH3, which is basically 2-chloropropane, right? Now, I hope if you have to attach an hydrogen halide HX to a symmetric or to a asymmetric, it will be clear to you both for both of the cases. Perfect. Now, let's do the mechanism for water, which is H2O. Now, this addition is done in the presence of catalyst. And what is a catalyst over here? Acid, right? Same thing. The very first reaction that happens over here is the water reacts with H positive, which is an acid, and forms hydronium ion H3O positive. Now the H3O positive is something like this. This is basically positive, and this is partial positive. Yeah, our coordinate bond has been formed over here. So let's take an example. Yeah. Now to this, you have this particular ion attached, which is positive. This is partially positive. Now the same thing, this negative charge will quickly go and attack this positive. Now the same thing, this double bond electron density will get attracted by this positively charged. So what will happen? You will have CH3, CH positive, CH3, and you have this OH, double bond over here, and one H. Now what will happen? This positive charge will get attracted by this oxygen electron, will form CH3, CH3, O, H, H. Since this is positive, it is going to lose its electron, and you will once again get that. And once again, you will get back to the compound, yeah, which is propane to ol, right? This particular reaction over here is the slow reaction. Right? Yeah, this is a slow reaction. And over here, this is fast, and even this is fast. Right? Similarly happens for a symmetric alkane also. In that, you can attach anything anywhere. Over here, we need to keep in mind that you have to attach the H with CH2 as per the Markovnikov rule. But when it is symmetric, you can attach anything anywhere. I hope this even electrophilic addition reactions of halogens or hydrogen halide or water molecule is clear for both symmetric and asymmetric alkenes. We'll stop over here, and in the next video, we'll talk about the oxidation and the reduction reactions. Stay tuned, keep learning, keep practicing, and don't forget to hit that subscribe button. Take care and have a good day. Bye bye.